So we're going to be beginning our nuclear energy unit, and it's very similar in some ways to our chemistry unit, but with some important differences. So we're still going to be using our periodic table. We're still going to be talking about protons and neutrons and electrons, but there are some important differences, and we'll talk about some of those. Let's just review a little bit as we get started in this unit. If we're thinking about what we learned in chemistry, the nucleus of an atom contains two things. So try to think about what those two things are. So inside of the nucleus there are protons and there are neutrons. Again, thinking back to our chemistry unit, think about the charges of those two subatomic particles. Protons, they have a positive charge. And so from what you know probably about like charges, just like magnets, for example, if you put the two south poles of a magnet together, what happens to them? They repel each other. If you put the north and south poles together, they attract each other. Okay, so if we think about the nucleus of an atom, if the protons are there and they're all positively charged, what should happen with two positive charges is they should repel each other. However, that's not what happens because there are also the neutrons. You could sort of think about the neutrons in the nucleus as sort of the glue that can help hold the nucleus together, hold all of those positively charged protons together so that it remains stable. And this is also the reason, if you look at your periodic table, as the number of protons increases for the various elements, you'll notice about the number of neutrons. Go ahead and look at it. What happens to the number of neutrons as the number of protons increases? Well, the number of neutrons increases as well. So the more protons you have in the nucleus of an atom, the more neutrons that you need to sort of hold it all together. If you think about it, if you look at elements higher up in the periodic table, you don't find elements with many protons but few neutrons. Usually the number of neutrons are equal to or greater than the number of protons. But for certain elements, larger elements, heavier elements, those that have more than 83 or so protons, even the extra neutrons cannot hold together that nucleus as effectively. And so these are the elements that we typically think about as the radioactive elements. Okay. And radioactivity and nuclear energy are two topics that go together. So let's think back again to chemistry. Isotopes. We learned about isotopes in chemistry. So what is an isotope? An isotope is sort of like a different version of an atom. It's an element that has an atomic mass that's different. And the reason the atomic mass is different is because there are a different number of neutrons. Remember, the number of protons for carbon, for example, is consistent. Okay? Carbon always has 6 protons. However, there can be some atoms of carbon that have different numbers of neutrons. Might have 6 neutrons, might have 7, might even have 8 neutrons. So those are different isotopes of carbon. And some of those isotopes are what we call radioactive. And what we mean by radioactive is that they are not stable. Okay? That the nucleus itself can break down. The nucleus itself can eject certain particles, and that can release energy, can even change the type of atom. So radioactive means an atom that has an unstable nucleus. And these unstable nuclei will eventually become stable by ejecting particles, by ejecting energy. And so we are going to be focusing on 3 main types of nuclear radiation. So one type of radiation is called an alpha particle. So sometimes a radioactive isotope ejects from it what we call an alpha particle. This is a type of radioactive decay. And an alpha particle is the same thing as a helium nucleus. And these alpha particles, they can't penetrate through substances very easily. Alpha particles can be stopped just by a simple sheet of paper. They cannot penetrate through that sheet of paper. So if we think about a helium nucleus, okay, if you find helium on your periodic table, helium has atomic number 2. Okay, it has an atomic mass of 4, meaning it has 2 protons, 2 neutrons. So we symbolize that with this symbol. He is the symbol for helium. The number on the bottom represents the atomic mass, 2. The number on the top is the atomic mass. I think I might have just said that wrong. The number on the bottom is the atomic number. Number on top is the atomic mass of this particle. So when an atom breaks down through what we call alpha decay, it emits or sends out an alpha particle. Okay? And that alpha particle is the helium nucleus. Other times, when a nucleus decays through nuclear radiation, it can eject what we call a beta particle. A beta particle is basically an electron. It's the same mass and same charge as an electron. And this electron is ejected from the nucleus of the atom. When we are writing a symbol for a beta particle, we write it like this. The E stands for an electron, which has a charge of -1. And as you remember from chemistry, electrons don't really have a mass, or a mass is so small we ignore it. So they don't change the atomic mass. Now that might sound a little strange to you when we talk about beta decay. How can an electron come out of the nucleus of an atom? There are no electrons in the nucleus of an atom. There's protons and neutrons. Well, if you ask that question yourself, that's a great question. What happens in beta decay is that a neutron, okay, actually turns into a proton and ejects an electron. So think about it. A neutron has a neutral charge. If it's emitting an electron, it gets rid of a negative, then it takes on a positive charge, making it a proton. So these beta particles that are ejected during beta decay, they can penetrate through substances to a higher degree than alpha particles can. A beta particle can go through a sheet of paper, but a thin sheet of metal such as aluminum can block a beta particle from penetrating. So that brings us to the third type of radiation, and that's gamma radiation. So when we're talking about gamma radiation, a nucleus is not emitting any actual particles, but it's emitting what we call gamma rays, which have no charge, no mass. Okay, this is basically energy. And gamma rays can penetrate significantly. They can penetrate through a sheet of paper, through a thin sheet of metal. It takes a thick piece of lead to actually block the penetration of gamma rays. They have a much shorter wavelength. And so when we think about the elements that we've studied, any element can have an isotope that's unstable, an isotope that's radioactive. But the larger elements, the elements with larger atomic masses, tend to be more unstable, tend to be more radioactive. So when we look at this illustration here, so what you'll see, all the light blue elements, they do have, like I said, unstable isotopes, but in general they have a very stable isotope as well. The green elements are the elements that have their most stable isotope is radioactive, but decays very, very slowly. We'll be talking about half-life later on in this unit, but the half-life of these green elements is measured in millions of years, so they do not decay very quickly. As we move up, we see some of these yellow elements here. Okay, and those yellow elements and the orange elements are progressively less stable. They decay much more quickly. Okay, they might have half-lives in the thousands or hundreds of years, all the way down to a half-life of a single day. Then we start looking at those red and those purple. Those are highly unstable elements, extremely radioactive. Even the most stable isotopes of those atoms, those elements, have half-lives less than a day, or even much, much less than that. So they decay very, very quickly. So different elements and different isotopes will decay, will break down at different rates. So when we are symbolizing alpha and beta particles and gamma radiation, we'll often use the Greek symbols. This is the symbol for alpha. This is an alpha particle. You can see it can be just blocked by a single sheet of paper. There we have the beta particles, which can go through the paper but will be blocked by aluminum. And then the gamma radiation, which can go through all but that sheet of lead. The tool that's used to measure radioactivity sometimes is a Geiger counter. It's a tool that detects radiation and sort of emits a sound every time it senses a certain level of radiation, and so you can use that to detect whether or not there's radioactivity in the area. I'm going to post this video. I won't show it to you here in this presentation in this video, but this is a presentation about Marie Curie. She's a Polish-French scientist who was working at the sort of end of the 19th century and beginning of the 20th century, who did significant work in the field of nuclear energy and radiation, and she has an interesting life story. She's the only woman to win 2 Nobel Prizes. She was the first woman to be awarded a Nobel Prize. So she has a very interesting life story, so I would definitely suggest watching this video, or if you're interested, reading a little bit about her as we move forward. So when an element's nucleus emits an alpha or beta particle, what happens is that it transmutates. That means it actually turns into a different element. Transmutation is the changing of one element into another. And let's look at how this happens. So if we have an atom of uranium-238, okay, so again, when we are using these symbols, we write the symbol of the element, write its atomic number below it, 92. We write its atomic mass above it, 238 for this isotope. And if this uranium atom is going to emit, I'll leave that up there a little bit longer for you. So if this uranium atom, uranium-238, is going to emit or give off an alpha particle, it goes through alpha decay, we would say. Okay, it's emitting this helium nucleus. So this helium nucleus, as we know, as we talked about a little bit earlier, has an atomic number of 2, has 2 protons, and it has an atomic mass of 4. So if the uranium emits and gives off this helium nucleus, think about what's going to be left. So what's going to happen to the atomic number of this uranium? If it's getting rid of this helium nucleus, it's getting rid of 2 protons, its atomic number is going to drop by 2. If it's getting rid of this helium nucleus, which has an atomic mass of 4, its atomic mass is going to also drop by 4. So when we subtract those numbers, what we find is that the atomic mass becomes 234, the atomic number becomes 90, and we know if the atomic mass is 90, this is no longer uranium. Okay? This is a new element. It has transmutated. Okay? And now it's thorium. Thorium has an atomic mass of 90. Okay? So you see sort of just another illustration of that. Okay, it's a little more visual here. So we have our uranium-238. It's giving off this helium nucleus, which is an alpha particle. Okay, so it's losing 2 protons, it's losing 2 neutrons, therefore it becomes what we call the daughter nucleus. This is called the parent isotope, or sometimes called the parent radioisotope. This is the daughter radioisotope, and it becomes thorium. Well, let's look at what would happen if this thorium nucleus, thorium-234, were to undergo beta decay. So a beta particle we talked about is basically an electron with no mass, okay, and a charge of -1. Remember, a neutron is being converted into a proton. Okay, so think about what's going to happen to the atomic number. Okay, so first, what's going to happen to the atomic mass, I guess? So if it's getting rid of this electron, which has no mass, its atomic mass is going to stay the same. But what's going to happen here? Remember, a neutron is converted into a proton. So if we're subtracting a -1, if a neutron is being converted into a proton, the atomic number is going to increase by 1. Again, so the atomic mass stays the same. The atomic number increases 1 because we subtracted a -1, which equals +1. So again, we have a new element formed. This thorium has been transmutated into a new element, palladium 91, 234. So again, if we look at this diagram, this shows what's going on. And in this beta decay, what you'll see is this neutron right here has changed into a proton. And it's emitted this electron. And so gaining a proton causes the atomic number to increase by 1. But that conversion, neutron to proton, doesn't change its mass. Now, the other thing I want to mention here is that these alpha decays and beta decays that we're talking about, they also emit energy. They also typically emit gamma radiation. Okay, but again, gamma radiation has no mass. Okay, so it doesn't change the atomic number or the atomic mass. Okay, here's another example. This is carbon-14, which is a radioactive isotope of carbon. Carbon-14 has 6 protons in the nucleus. It has 8 neutrons. When it goes through a beta decay, this neutron is converted into a proton and an electron is released. So carbon-14 transmutates into an element that has 7 protons now because of that change and 7 neutrons, making it nitrogen. Nitrogen is the element that has 7 protons. Its mass is unchanged, and that's a beta decay. This is a TED-Ed video that I'll post. Just sort of gives an overview of radioactive decay. It's a little more visual, but that might help reinforce some of the things that we talked about. Now, before we finish up with this video, one thing to keep in mind is, well, how is nuclear energy, this unit, different from chemistry? Think back to chemistry. The interactions we were talking about in chemistry were interactions between two elements, but it was the electrons of those elements that were responsible for how these molecules were behaving, how they were bonding with other molecules, other elements. And so chemistry is focused on the electrons. But here, when we're talking about nuclear energy, we're talking about changes happening in the nucleus, emitting alpha particles and beta particles. Nuclear energy, hence the name nuclear energy, focuses on changes happening in the nucleus. So we're going to stop things here for today, this first section, and we'll continue on talking about decay chains later on in the week. So thanks for watching the video.